Hey folks, welcome to another set of Chemistry 1 video notes. To start out Unit 6, we'll be talking about how to balance chemical equations. This lesson covers standards C.1.6 and C.4.3, which ask you to demonstrate an understanding of the law of conservation of mass through the use of particle diagrams and mathematical models, and to be able to balance chemical equations and use the law of conservation of mass to explain why this must be true. I know you've learned this a couple of years ago, but do you remember what the law of conservation of mass says? The textbook definition is that in any ordinary physical or chemical change, matter cannot be created nor destroyed, only rearranged. That's a very good definition, but it might not be very practical or useful to you. So if we break it down and simplify it a little bit, we might get a definition like this. Before, during, and after a physical or chemical change, you always have the same amount of each type of atom, since we don't create new atoms or destroy old ones. Furthermore, the total mass before a change is the same as the total mass after the change. That's probably a little more useful to you, but if you're still struggling with it, here's an even simpler definition. Particles are not created or destroyed. They just get rearranged to form new substances. We should have the same number of atoms for each element and the same total mass before, during, and after a change occurs. Before we go much further, let's review what a chemical equation looks like. On the left side of the arrow, or the yield symbol, we have the reactants. These are the substances that we start with. On the right side, we have the products. These are the substances that we end with. These substances are represented by their chemical formulas. If you'll remember from a while back, these chemical formulas often have subscripts, which tell us how many atoms of each of those elements we have in one molecule of that substance. If there is no subscript, it means that we only have one atom of that element in that molecule. Right next to those subscripts are another little symbol that will become really important later on in this class. These are called state symbols. They tell us whether the substance is a solid, a liquid, or a gas, or if it's dissolved in water, otherwise known as aqueous. Finally, the really important part for balancing these equations are the coefficients. These are the big numbers before a chemical formula. These tell you how many molecules or moles of that substance your reaction will involve. If it's on the reactant side, that's how many molecules you need in order for that reaction to occur. If it's on the product side, that's how many molecules you're going to produce each time that reaction occurs. So when reading this chemical equation, it might sound something like this. 2 moles of solid mercury 2 oxide will yield 2 moles of liquid mercury and 1 mole of oxygen gas. So why does all of this matter? That's a great question. The law of conservation of mass is the reason why having a balanced chemical equation is so important. If your equation isn't balanced, it simply does not reflect what's happening. A balanced equation allows you to calculate how much of your reactants you need to produce a certain amount of products. It'll help you determine how easily you can speed up or slow down that reaction, or in which ways certain factors will affect the speed of the reaction. Contrary to popular belief, an unbalanced chemical equation does not result in explosions. It simply results in inaccurate calculations and thoroughly unexciting reactions, or even no reactions at all. A balanced chemical equation follows the law of conservation of mass. If you think of balanced equations like recipes, it makes a little bit more sense. I found this super easy peanut butter cookie recipe online. So easy, in fact, that I could probably bake some and they'd turn out fine. It calls for 1 cup of sugar, 8 ounces of peanut butter, and 1 egg. This recipe yields 12 peanut butter cookies. Notice these numbers are different. We have 1 cup, 8 ounces, 1 egg, gives us 12 cookies. If this equation were unbalanced, say we just said 1 all the way across, it wouldn't work quite the same way. 1 cup of sugar, 1 ounce of peanut butter, and 1 egg combines together to make one pile of disgusting goop, not 12 tasty peanut butter cookies. It's the same concept with chemical equations. It's not that a reaction is going to blow up. It's just that they won't turn out the way we're expecting. Before we start balancing equations, here are some things you need to know. Our goal is to make sure that there's the same number of atoms of each element on the reactant side as there are of that element on the product side. Sometimes one of our elements, usually oxygen if I'm being honest, exists in multiple substances on the same side of our equation. It's really important to take special note of that when that's the case, and to make sure that you add up the total number of atoms of that element on that side of the equation, not just the atoms in the formula that you just changed a coefficient for. No coefficient or no subscript does not mean that that molecule or element doesn't exist. The fact that we wrote it down in the equation tells us that it's there. If there's no coefficient or subscript, it's just because there's only one of those molecules or atoms. A long time ago, chemists realized that it's a little bit redundant to both write down a chemical formula and specify that it exists in the equation. So we just don't write the ones. And last but not least, if you have a coefficient or subscript outside of some elements that are enclosed in a parentheses, you treat that just as you would with math. Distribute it. Everything inside this parentheses will get multiplied by any coefficients directly to the left of the parentheses or any subscripts directly to the right of them. We're going to do some example problems in a few, and when we do that, these steps here will run across the screen as I'm performing them. But go ahead and write them down in your notebook as I read through. The first step to balancing an equation is to write the chemical symbols for all of your elements underneath the reaction arrow. Basically, make a vertical list of the element symbols you have. We're going to use that list to keep track of how many atoms of each of those elements we have on either side of the arrow. Next, count up how many atoms of each of your elements you have on the left or reactant side. Write those numbers on the left side of their appropriate element symbols. Then do the same for the right or the product side. Next, evaluate those numbers. Are each of the numbers on the left equal to their counterparts on the right? If so, congratulations, you're finished. Pack up and go home. If not, identify one of those elements that is lacking on one side or the other. Go back to the top and add 1 to the coefficient on the correct side of your equation right before a formula that includes that element. Remember, no coefficient means it's 1. So if you add 1 to the one that's already there, you get 2. After you change a coefficient, do not change any more coefficients until you stop and recount your atoms. Sometimes you think, oh, I can go ahead and change a couple of coefficients at a time and then count. But usually what happens is the first one might balance the equation, and then the second one unbalances it. So you're stuck in this loop of messing up your equation every time you try to balance it with more than one coefficient at a time. After you've recounted, go back to step 3, evaluate those numbers again, change coefficients if you need to, go back to step 4, recount them, and keep repeating steps 3 and 4 until you finally get your equation balanced. Some helpful hints before we set off to go do some examples. Make sure you keep track of the atoms the way I described above. Even if it's not your favorite way, I need to see it that way to see that you've done the work and understand what it is you're doing. If you're a pretty visual person, go ahead and draw the molecules as you balance. Remember to start out with 1 of each molecule because no coefficient means 1. And then as you change coefficients, draw more molecules. Seeing those molecules and the atoms within them is extremely helpful to some people. If you've come up with your own way to track the numbers that works, feel free to also use that way. When you're keeping track of the numbers of atoms on your list below the equation, do not just multiply those numbers by the coefficients you changed. This is usually okay for really simple equations, but it'll get you into trouble with even slightly more complicated ones. Remember, you're counting the number of atoms of each element on that whole side of the equation. So if you've got an element that exists in multiple substances, you have to be sure to include all of them in your count. When picking which element to try to balance first, pick one that exists in a fairly large molecule. Save the simple molecules like O2, H2, or just single elements for last. You can change the coefficients for the molecules or atoms that only have one element and that'll only change that element's number of atoms. It won't affect any other elements. That's why they're the best to save for last. Finally, if you balance an equation and all of your coefficients are divisible by a common factor, simplify it. For example, if your coefficients are 3, 3, 6, and 3, that'll reduce down to 1, 1, 2, and 1. That doesn't mean you're wrong, per se, because it is balanced, but we want the simplest ratio of the molecules in our balanced equation. All right, let's head over to the board and do a few examples. Be sure to follow along and write those examples as I complete them. You'll also see on your screen the step that I'm on and a visual representation of the molecules as I balance the equation. Okay, so our first equation is magnesium plus oxygen gives us magnesium oxide. The first step is to write down the symbols for our elements. So we have Mg and we have O. Second step is to count up the reactant side. We have 1 Mg right here, and we have 2 O's. On the product side, we have 1 Mg and 1 O. So step 3, we check, is that balanced? Well, we have 1 and 1, so this one's good. But 2 and 1 means that our oxygen is lacking on the right side. So we need to change a coefficient up here on the right side of our equation. The only coefficient we have changed is the before the MgO. So if we want 2 O's, we put a 2 up here, and then we stop and recount. So that gives us now there's 2 Mg's, and now there's 2 O's. So now we go back. Step 3, again, are we balanced? 1 and 2, 2 and 2. Well, the magnesium's not balanced now. So we could make this one 2 up here. That would give us now 2 Mg's, and that would make us balanced. 2 and 2 and 2 and 2. It's important to know they don't all have to be 2, but the magnesium, if it's 2 on one side, has to be 2 on the other. If the oxygen were like 6, that'd be fine. It would just have to be 6 on both sides. All right, our second example is the combustion of methane. So we take methane, combine it with oxygen, and we get carbon dioxide and water. So our first step is to write down the symbols for our elements underneath the arrow. So we have carbon, hydrogen, and oxygen. Second step, count them up. Left side, we have 1 carbon. We have 4 hydrogens, and we have 2 oxygens. On the right side, we have 1 carbon, right here. We have 2 hydrogens from over there. And we have, this is one of those tricky ones where oxygen's in more than one place, so we have to pay attention. 2 oxygens plus this 1 oxygen gives us 3. So step 3, evaluate those numbers. Are they balanced? We have 1 and 1, that's good. 4 and 2, that's not good. 2 and 3, also not good. Now you got to choose. Do you want to try to balance the H's or the O's first? On the left side, the O is all by itself. So we might want to save that for last because it'll become easier later. So let's balance the H's first. I have 2 hydrogens on the right side, but I need 4. So if I change this coefficient from a 1 to a 2, that'll now give me 4 hydrogens and 2 oxygens plus these 2 oxygens over here. So that gives me 4 oxygens. Notice I didn't put a 2 up here and just multiply this 3 times 2 to get 6 because that's not right. It's my total number of atoms. So we have these 2 plus those 2 gives us 4. Now the only thing we have to do is balance our oxygens because we're good. 1 and 1 for carbon, 4 and 4 for hydrogen, 2 and 4 for oxygen. We need more on the left side. So to get more here, we'll put a 2 up there. And that'll make this 4. Now we evaluate again. 1 and 1, 4 and 4, 4 and 4. We're balanced. All right, our last problem is a little bit more complicated. You'll notice we don't have any of them that are just single elements. And we have some of them that have parentheses. So let's get going. We have barium. We have oxygen. We have hydrogen, iron, and sulfur. Step 2 is to count them up. So on the left side over here we have 1 barium. We have 1 oxygen inside the parentheses, but there's a 2 outside the parentheses. So that means we have 2 oxygens. Same goes for the hydrogen. Our iron has a little 2 subscript beside it, so we have 2 irons. Sulfur's inside a parentheses with a 3 on the outside, so there's 3 sulfurs. And we missed one. There's an oxygen up here. This is what I was telling you about earlier. Sometimes we have something like oxygen or another element that exists in multiple substances. And we have to make sure we're counting all of the atoms we have, not just from one substance. So let's go back and recount that one. We have these 2 plus 4 oxygens times its 3 outside the parentheses is 12. So 2 plus 12 is 14. On the right side, we have barium up here with still just 1. There's 1 sulfur. There's 4 oxygens here plus 3 from over there, so there's 7. Hydrogen, there's 3 right from there. And iron, there's only 1. All right, so before we talked about we want to save the single element one just for last. We don't have any of those, so we can just pick a random one to start with. I think I want to fix my irons first because it looks pretty easy to solve. I have 1 on one side, 2 on the other. So if I want to change that, I can put a 2 up here because that would give me 2 times my 1 iron would get me 2 irons, and now the irons are balanced. But we have to recount everything else too. So we have our 2 times this 1 oxygen is 2 times the 3 outside the parentheses. So 2 times 3 is 6. There's 6 oxygens over here, plus these 4 give us 10. This is where it gets tricky because we have to remember to count all of the oxygens we have, not just the ones we just changed. And that also changed our hydrogens. We've got 2 times that 1 hydrogen is 2 times the 3 outside the parentheses is now 6. And that's the damage we did with that 2. So now we have 3 and 1, 2 and 2, 2 and 6, 14, 10, 1 and 1. We're still not quite balanced. Let's fix our sulfurs next. That looks pretty easy too. So I need to get 3 sulfurs on the right side because I have 3 on the left side. The only molecule up here that has sulfur is barium sulfate. So if I choose to put a 3 in front of that, I know that's going to change my sulfur to 3 and get that balanced. It also changes my barium to 3 and my oxygen to 3 times 4 is 12, plus this 6 from over here is 18. So in doing that, we messed up our barium, so let's fix the barium on this side. I'll put a 3 in front of that, and that gets me 3 times my barium is 3 bariums. That also changes my O's, because 3 times that O is 3, times 2 is 6, plus these 12 over here is now 18. And I've got 3 times my H is 3 times that 2 is now 6. Now we stop, make sure we're balanced. We got 3 and 3, 18, 18, 6, 6, 2, 2, 3, 3. And that's it. That wasn't so hard, now was it?
All right, folks, that's it for this lesson. I hope this video will help you become a pro at balancing equations. If you have any questions, as always, please ask.